Picture yourself as a government official in ancient China, around 100 BCE, during the Han Dynasty. You're responsible for collecting taxes from thousands of farmers across multiple provinces. You need to calculate grain production from irregularly shaped fields. You need to determine fair tax rates. You need to solve complex distribution problems involving rice, silk, and labor. You reach for your copy of the 9 chapters on the mathematical art. This book contains 246 problems covering everything from land surveying to engineering to commerce. It has methods for solving systems of linear equations, calculating square and cube roots, and working with fractions. It presents algorithms that Europe won't discover for another 1,000 years. And here's the stunning part. While Europe was still using Roman numerals and struggling with basic arithmetic, Chinese mathematicians were solving problems that wouldn't appear in European textbooks until the Renaissance. Welcome to Math's Whisperer, where we uncover the hidden stories of mathematics. I'm your host, and this is Season 2, Episode 4. Today, we're traveling to ancient China to discover how one mathematical textbook changed an empire and reveals a civilization whose mathematical sophistication was centuries ahead of the West. The 9 chapters on the mathematical art, known in Chinese as Zhu Zheng Xuan Shu, is one of the most important mathematical works in history. Yet most people in the West have never heard of it. This alone tells us something about how we've understood the history of mathematics as if it only happened in Greece and Europe. And in reality, profound mathematical thinking was happening simultaneously across the world. The 9 chapters was compiled around 200 BCE to 100 BCE. Though it draws on mathematical knowledge stretching back much earlier, we don't know who wrote it. Unlike Greek mathematics, which celebrated individual geniuses like Euclid or Archimedes, Chinese mathematics was more collective, more practical, more focused on solving real problems than on abstract proofs. The book is organized into 9 chapters, each focused on a different practical application. This structure itself reveals something important. Chinese mathematics was deeply embedded in the needs of society. Mathematics wasn't pursued for its own sake, but as a tool for running an empire. Let me take you through what's in these 9 chapters, and as we go, notice how sophisticated this mathematics is. Chapter 1 is called Field Measurement. It deals with calculating areas of fields. Simple enough, right? But Chinese fields weren't neat rectangles. They were irregular shapes created by natural landscape features. The 9 chapters provides methods for calculating areas of triangles, trapezoids, circles, and complex, irregular shapes. It gives formulas like, the area of a triangle is half the base times the height. The area of a circle is approximately 1/12 the square of the circumference. This last formula, while not perfectly accurate, shows they understood the relationship between a circle's circumference and area. They used these formulas for taxation. If you knew the area of a farmer's land and the expected yield per unit area, you could calculate fair taxes. This wasn't just theoretical mathematics. It was essential for running an agricultural empire. Chapter 2, Millet and Rice, deals with proportion problems. These are problems about exchanging goods at different rates. If you can exchange 5 bushels of millet for 3 of rice, how much rice can you get for 13 bushels of millet? This sounds simple, but the 9 chapters systematizes the method of false position and other techniques for solving proportion problems. They were doing what we now call cross-multiplication and solving for unknowns, and they were doing it over 2,000 years ago. Chapter 3 Distribution by progression. Covers arithmetic and geometric sequences. How do you distribute goods among people in proportion to their rank or contribution? These problems involve what we now call arithmetic progression sequences, where each term differs from the previous by a constant amount. One famous problem asks, if you're distributing grain to workers, with the top worker getting the most, and each subsequent worker getting less by a fixed amount, and you know the total grain and number of workers, how much does each person get? This requires understanding of series summation. The 9 chapters provides algorithms for solving these problems that wouldn't appear in European mathematics until the late Middle Ages. Chapter 4. Short width deals with finding dimensions when you know certain measurements. For example, if you know the area of a rectangle and the difference between its length and width, can you find the actual dimensions? These problems require solving quadratic equations. And here's where it gets really interesting. The 9 chapters doesn't just give you the formula. It provides a systematic method using geometric reasoning and manipulation that essentially works like our quadratic formula, but expressed differently. Chinese mathematicians were solving quadratic equations routinely when European mathematicians were still debating whether negative numbers made sense. Chapter 5. Construction consultations focuses on calculating volumes. How much earth is needed to build a dam? How much material to construct a wall? These problems require calculating volumes of complex three-dimensional shapes, pyramids with rectangular bases, truncated pyramids, wedges, and more. The formulas given are remarkably accurate. For the volume of a pyramid, they give 1/3 the base area times the height. This is exactly correct and shows deep geometric understanding. Chapter 6. Fair distribution deals with sophisticated proportion. Problems involving multiple goods and exchange rates. These are early examples of what we'd now call systems of linear equations. One problem asks, different types of grain have different values. You're distributing grain to workers based on their work quality. Given complex relationships between grain types and worker categories, how do you distribute fairly? The 9 chapters provide systematic methods for solving these problems that anticipate matrix methods developed in Europe much later. Chapter 7. Excess and deficiency focuses on a method called the rule of double false position. This is a clever technique for solving equations when you don't know the answer but can make guesses and see if they're too high or too low. Here's how it works. You guess an answer. You check if it's too big or too small and by how much. You guess again. Then, using the 2 guesses and their errors, you calculate the actual answer. This method was used in Europe, but it appeared there in the 13th century, over 1,000 years after the 9 chapters. European mathematicians called it the Chinese rule or rule of false position, acknowledging its Eastern origins. Chapter 8. Rectangular arrays is perhaps the most mathematically sophisticated chapter. It deals with systems of linear equations, multiple equations with multiple unknowns. Here's an example problem. You have 3 types of grain. 3 transactions involve different amounts of each grain type, totaling different amounts of money. How much does each grain type cost? This requires solving a system of 3 equations with 3 unknowns. The 9 chapters presents a method. That's essentially Gaussian elimination using systematic row operations to solve systems of equations. European mathematicians wouldn't develop this method until the 18th century. About 2,000 years later, the Chinese method uses counting rods arranged on a counting board to represent the coefficients of equations. By manipulating the rods according to specific rules, they could solve complex systems. It's matrix algebra before matrices were formally invented. Chapter 9. Right triangles covers the Pythagorean theorem and its applications. But here's the crucial point. The Chinese knew the Pythagorean theorem independently of the Greeks. They called it the Gugu theorem, and they used it extensively for surveying and construction. They didn't just know the theorem, they had multiple geometric proofs of it. One particularly elegant proof, attributed to the 3rd century mathematician Liu Hui, uses a dissection argument that rearranges shapes to show the relationship holds. Chapter also contains approximation methods for calculating square roots to any desired precision. These iterative methods are sophisticated algorithms that produce increasingly accurate approximations. Now, let's talk about Liu Hui, one of the greatest commentators on the 9 chapters. In 263 CE, Liu Hui wrote an extensive commentary explaining and expanding the 9 chapters. His commentary is almost as important as the original text. Liu Hui didn't just explain how to use the methods, he explained why they work. He provided geometric proofs and deeper mathematical reasoning. He was bringing the rigor of mathematical proof to a text that was primarily algorithmic. One of Liu Hui's remarkable achievements was calculating pi. He used a method of inscribing polygons within a circle, calculating their perimeters, and using these to approximate the circle's circumference. By using a polygon with 3072 sides, he calculated pi to 5 decimal places, 3.14159. This is extraordinarily accurate for the 3rd century. European mathematicians wouldn't achieve this level of precision for over 1,000 years. What makes Chinese mathematics distinctive is its character. While Greek mathematics emphasized logical proof and abstract reasoning, Chinese mathematics emphasized algorithms and computation. The 9 chapters doesn't prove the Pythagorean theorem philosophically. It shows you how to use it to measure land and build structures. This doesn't make it less sophisticated. It's a different approach to mathematical knowledge. The Chinese valued methods that work, that can be taught systematically, that solve real problems. Their mathematics was embedded in the practical needs of running a massive, complex empire. The 9 chapters was used as a textbook for training government officials for over 1,000 years. Civil service examinations tested candidates on problems from it. Generations of Chinese mathematicians learned from it, commented on it, and extended its methods. The influence spread beyond China. Korean and Japanese mathematicians studied the 9 chapters. It shaped mathematical development across East Asia. When European Jesuit missionaries arrived in China in the 16th and 17th centuries, they were shocked to discover sophisticated mathematics they hadn't expected. Some of these Jesuits, like Matteo Ricci, brought European mathematical knowledge to China, but also brought Chinese mathematical knowledge back to Europe. The exchange wasn't one way. European mathematicians learned from Chinese methods, though this is often downplayed in Western histories of mathematics. There's a tragic irony here. For centuries, Western historians of mathematics focused almost exclusively on Greek and European achievements. The narrative was, mathematics began with the Greeks, was preserved by Islamic scholars during the European Dark Ages, and then flourished again during the European Renaissance. This narrative ignored China, India, and other civilizations completely. It created the false impression that mathematical sophistication was uniquely Western. Students learned about Pythagoras but not about the independent discovery of the Pythagorean theorem in China. They learned about Gaussian elimination but not about the Chinese method that preceded it by 2 millennia. This is changing. Modern historians of mathematics recognize that mathematical knowledge developed independently in multiple civilizations. There's no single source of mathematics. Different cultures approached mathematical problems differently, and each approach has value. The 9 chapters teaches us several important lessons. First, practical mathematics can be profound mathematics. The problems in the 9 chapters emerge from real needs: taxation, construction, trade, but solving them requires sophisticated mathematical thinking. You don't need to pursue mathematics for purely abstract reasons to develop deep mathematical knowledge. Second, different approaches. 2. Mathematics are valuable. The Chinese algorithmic approach and the Greek proof-based approach are both legitimate ways of doing mathematics. Modern mathematics incorporates both. We want methods that work, and we want to understand why they work. Third, mathematics is universal, but not uniform. Multiple civilizations discovered similar mathematical truths independently. The Pythagorean theorem is true whether discovered in Greece or China. But the way different cultures approached mathematics, the problems they prioritized, and the methods they developed varied based on their needs and values. Fourth, mathematical knowledge is often transmitted silently. When European mathematicians developed methods similar to those in the 9 chapters centuries later, were they rediscovering independently, or were they influenced by knowledge transmitted through Islamic scholars, traders, and travelers? Often, we don't know. Knowledge spreads in complex ways that aren't always documented. Finally, the 9 chapters reminds us to question our narratives. When we learn the history of mathematics, whose history are we learning? What voices are missing? The standard narrative left out Chinese mathematics for centuries, not because it wasn't sophisticated, but because Western scholars weren't looking for mathematical achievement outside Greece and Europe today. You can study English. Translations of the 9 chapters. Scholars have analyzed its methods and recognized their sophistication. The algorithms it presents are taught in history of mathematics courses. Liu Hui's commentary is studied for its mathematical insight. But imagine if we'd known about the 9 chapters all along. Imagine if students learning to solve systems of equations were told, this method was first systematized in China over 2,000 years ago. Imagine if the Pythagorean theorem were introduced as a theorem discovered independently by multiple civilizations. Our understanding of mathematics itself would be richer. We'd see mathematics as a human endeavor, something that emerges when intelligent people tackle challenging problems, regardless of culture or geography. We'd appreciate the diversity of mathematical thinking rather than seeing one tradition as the only legitimate source. The 9 chapters on the mathematical art stands as a monument to human ingenuity. It solved practical problems facing an agricultural empire, and in doing so developed mathematical methods of stunning sophistication. It was used continuously for over a millennium, shaping the mathematical education of countless scholars and officials. And it reminds us that while Europe was fumbling with Roman numerals, while Greek mathematics was being forgotten in the West, mathematical knowledge was flourishing in China, creating tools and methods that we still use today. So next time you solve a system of equations, remember you're using a method that Chinese mathematicians perfected 2,000 years ago. Next time you calculate the area of an irregular shape, remember Chinese surveyors were doing the same calculations to assess taxes in the Han Dynasty. Mathematics belongs to all humanity, and the 9 chapters proves it. If you're fascinated by the global history of mathematics and how Different civilizations solved the same problems in different ways. Subscribe to Maths Whisperer. We're releasing daily episodes exploring mathematical thinking across cultures and centuries. Tomorrow, we're discovering how the Mayan civilization invented zero independently and created a calendar more accurate than the one Europe was using 1,000 years later. Hit subscribe, ring that bell, and comment. What other mathematical achievements from non-European civilizations would you like to learn about? Let's keep exploring mathematics together, one whisper at a time.